Hello. In this example, we're going to go over the NVT Ensemble for GOMC using MoSDeF to build the files. My name is Brad Crawford. I would like to take this time to thank Wayne State University for support for this research, as well as NSF for these 3 grant numbers, which encompass GOMC and MoSDeF projects. The first thing we're going to do is import the Python packages we need, including the MoSDeF charm writer and GOMC control file writer. We're going to select the force field we want, which is the trap UA force field, and we can set it as only a string and not a dictionary since we're using the same force field for all the molecules in the system. Set the liquid box length, and that's in all dimensions, X, Y, and Z. You can set them differently as you want, but that's how we're going to do it here. We're going to set the liquid density in kilogram per meters cubed at 642, which is the ratio average of the experimental data, at least roughly. We're going to set the pentane and hexane mole ratios at 50-50, which it will be using pentane and hexane in this example. Run it with Shift-Enter. Next, we're going to create the pentane-hexane molecules with residue names and minimize their structures using the force field. We're going to import the mol2 files or the molecules from the mol2 files, which are located in the files directory for pentane and hexane. We're going to name them pen and hex for their residue names, and then minimize their structures using the force field we just selected. We're going to make a few lists, one containing the molecules, pentane and hexane, the residues for pentane and hexane, and the molecular ratios for pentane and hexane. We're going to build the simulation box, or box 0, using the mole list we just made, inserting the density that we want and the mole ratio we want, and using the box length that we set earlier in angstroms divided by 10, which gives nanometers as standard units for this function. And if we wanted different X, Y, and Z, we could set them here, since this is X, Y, and Z. Run that. We're going to build the charm object using the box we just built, a string to name the PSF and PDB files, a string to name the force field file or .imp file, the force field that we made earlier via a selection in string, i.e. the trap UA force field, and then the residues list we made. You get some information. Here you'll see you get BD1 for the names, and that stands for bead 1, 2, 3, 4, 5 for pentane, and bead 1 through 6 for hexane. Since we didn't set the bead dictionary, you get a BD as default. Lastly, we're going to write the force field, PSF, and PDB files here. And then we're going to write the GOMC control file using the charm object, whatever we want to name the control file, selecting the ensemble, number of steps, and temperature. And in this example, we're going to use electrostatic and Ewald equals false. What that does is, since in the trap UA force field, at least for N-hexane and N-pentane, there is no charges on the beads, so everything is charge neutral. So we don't really need to calculate electrostatics or Ewald since there's nothing to calculate. And this will help speed up the calculations. We'll run that. Get some information, and then it completed. We'll do a terminal window example of part 6. To get in the right directory, we cd and then drag and drop Python file that we want to use. Delete the file name, just leaving the path, and hit enter. And note here, this Python in the Jupyter Notebook file that we just used are the exact same files. They just have different extensions. To run the Python file, we type Python and NV tab and should fill most of it, and then .py. Note that I already have the Python environment running that contains the MoSDeF package. Hit enter. You can see it run. It will give us some warnings, but that's expected because we're generating beads and using the UA force field. You can see the files build here. Next, we want to run the GOMC simulation. So we go to the GOMC folder. And if you build it using the GOMC instructions, you'll get a bin folder. We can click on that. In this case, we want to run the NVT portion or binary. And I'm going to use the CPU version because I'm on my Mac. We can click and drag and drop this in the window. Or you can type the path if you know it, plus P2 for 2 cores. And then we want to run the IN underscore NVT. And then we want to write that to an out.data file as a log file. We'll hit enter. It's running. You can see the files building. We'll open the bulk data file. You can see generated some data. So it looks like simulation ran. Thank you for watching and have a good day. The references for some of this work is as listed here. The reference numbers are kept the same through the examples to make it easier